All right, let's jump right into today's explainer. We're tackling something that honestly looks like straight-up magic, how you can bend a stream of water without even touching it. And to figure that out, we need to dive into one of the most important ideas in all of chemistry, molecular polarity.
Seriously, have you ever seen this for yourself? A stream of water just bending through the air? It seems like it should be impossible, right? Well, it's a completely real phenomenon, and the science behind it is just fantastic.
You can even try this at home. Just get a thin stream of water going from the tap, then take a balloon, rub it on your hair to get it all staticky, and bring it close. You will literally see the water curve towards the balloon. This isn't some kind of trick, it's pure science. And to really get what's going on, we have to shrink down to a level you can't even see, the molecular level.
Okay, section 1, a bend in the water. Let's figure out what's causing this bizarre effect.
So what is happening here? The key to this entire puzzle is hiding inside one single water molecule. The unique way that one tiny molecule is built when you get billions of them together is what causes that entire stream of water to bend.
Right. Section 2, unevenly charged molecules. You can kind of think of these as nature's own tiny magnets.
This brings us to a really important concept, the bond dipole. Now, you know that atoms inside a molecule are held together because they share electrons. But what happens if that sharing isn't exactly equal? If one atom is a little greedier and pulls those electrons closer, it creates a slightly negative end and a slightly positive end. That separation of charge is a bond dipole.
So how does this whole thing work with water? Well, the oxygen atom is what we call highly electronegative. Just think of it as an electron hog. It pulls the shared electrons away from the two hydrogen atoms. This gives the oxygen part of the molecule a slight negative charge, and it leaves both of the hydrogen atoms with a slight positive charge. Now, a single water molecule actually has two of these bond dipoles. But the real key is what happens when they're combined. If those individual little dipoles add up in a way that gives the entire molecule a positive side and a negative side, it creates something called a net dipole. And that, my friends, is the very definition of a polar molecule. And this is where the molecule's shape becomes absolutely critical. You see, a water molecule isn't just a straight line. It has a distinctive bent V shape. Because of that angle, the two bond dipoles don't pull in opposite directions and cancel out. It's like a game of tug-of-war where the two ropes are pulling at an angle. They create a combined pull in one general direction. That combined pull is water's net dipole.
Okay, on to section 3. Shape is everything. This is all about the symmetry factor. So this seems kind of simple, yeah? If a molecule has polar bonds, then it has to be a polar molecule, right? Well, maybe not so fast. Is that always true?
Not always. Let me introduce you to carbon dioxide, or CO2. It actually has strong polar bonds, just like water. And yet, the CO2 molecule itself is completely nonpolar. So how is that even possible?
The difference boils down to just one thing: shape. Water's bent, asymmetrical shape lets its bond dipoles add up to create a net pull. But carbon dioxide, it's a perfectly straight, linear, and symmetrical molecule. That symmetry is the reason it's nonpolar, and it changes everything.
In a CO2 molecule, you have two oxygen atoms pulling electrons away from the carbon atom in the middle. But because the molecule is a straight line, they pull with equal force in perfectly opposite directions. It's a perfectly balanced tug-of-war, a total stalemate. The forces cancel each other out completely, leaving no net dipole at all.
And that is what makes a molecule nonpolar. It has no net dipole. Now, this can happen because its bonds weren't polar to begin with, or, like we just saw with carbon dioxide, because its symmetrical shape makes all those individual bond dipoles just cancel each other out.
So here is the crucial takeaway. This is the one rule to remember. For a molecule to be polar, it needs to have two things: polar bonds and an asymmetrical shape. That's it. That's the secret. All right, section 4, the polarity playbook. Let's give you a quick guide on how to predict this for yourself.
You can figure this out with a simple 3-step process. First, just check for polar bonds. If you see different types of atoms bonded together, chances are the bond is polar.
Second, determine the 3D shape. Just ask yourself, is it symmetrical? Third and finally, see if the dipoles cancel out. If the shape is symmetrical, they almost always do, and you've got yourself a nonpolar molecule.
Here are a few common examples to look out for. These highly symmetrical shapes, linear, trigonal planar, or tetrahedral, they almost always lead to a nonpolar molecule, as long as all the atoms on the outside are the same. You can see it here with CO2 and even with more complex molecules like CCl4. That perfect symmetry cancels everything out.
In our final section, number 5, why polarity matters. Okay, so what? What are the real-world effects of all this?
Well, let's go back and solve our original mystery. The stream of water bends because the charged balloon attracts the slightly positive ends of all those polar water molecules, pulling the whole stream towards it. But water's polarity explains so much more. It's the reason water is called the universal solvent. Its polar ends can literally surround salt crystals and pull them apart. And, fascinatingly, this idea of polarity is also connected to why both water and carbon dioxide are such important greenhouse gases.
But hold on, that leaves us with one last really interesting puzzle. We just established that CO2 is nonpolar. It has no net dipole. Yet, for a molecule to be a greenhouse gas, it has to be able to absorb infrared energy from the sun, which requires a changing dipole. So, how can nonpolar carbon dioxide do that? That is a fantastic question, and it's a mystery for another explainer. Thanks for joining us.